Welcome to The Explainer. Today, we're taking what usually looks like a dense, boring geometry chapter and turning it into your ultimate structural blueprint. Think of the Cambridge 0580 exam like a massive, high-stakes football pitch. To win, you need formation, you need tactics, and you absolutely need flawless execution to outplay the defense, which, in this case, are those tricky question barriers examiners put up. Whether you're cramming for that exam or just want to decode the math behind the physical world, we're breaking down the exact rules that govern everything from sharp angles to massive architectural drawings. We see students all the time. Let's call them Alex and Sam. Alex overloads answers with raw mathematical facts but does zero analysis. Sam just rushes and completely misses the command word requirements. Today, we fix both of those approaches. Here is our tactical playbook for today. We'll start with building blocks, lines, and angles. Next, triangles, types, and properties. Then we'll tackle quadrilaterals, polygons, and circles. We'll follow that by folding into 3D with nets. And finally, we'll finish strong with construction and scale drawings.
Okay, Section 1, building blocks, lines, and angles. Let's get right into the foundation. Let's start with angles. In the exam, an angle is essentially the measure of rotation between two intersecting lines. You've got to know these definitions cold. An acute angle is small and sharp, sitting right between 0 and 90 degrees. A right angle is completely unbending, exactly 90 degrees. Now push past that 90-degree mark and you get an obtuse angle, stretching all the way up to 180. Keep sweeping past a straight line, into that 180 to 360-degree territory, and boom, you've created a reflex angle. Knowing these strict boundaries is your absolute first step to geometrical fluency. When the command word says identify, this is the exact vocabulary the examiner is looking for. Now, how do straight lines actually interact? Think of railway tracks, parallel lines that can continue to infinity in either direction without ever meeting. In a diagram, you'll often see these marked with matching little arrows. In stark contrast, perpendicular lines deliberately crash into each other to form a perfect 90-degree right angle. If you drop a line straight down from the top of a triangle to its base at a right angle, that perpendicular line is its exact height. Before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Section 2, triangles, types, and properties. Moving on to three-sided shapes.
Triangles can be classified by their internal angles, sure, but also by their side lengths. This is where students like Sam rush and lose easy marks. An equilateral triangle is perfectly balanced, 3 equal sides, 3 equal angles. An isosceles triangle has 2 equal sides, meaning the angles opposite them match exactly as well. And then, we have the scaling triangle, the total rebel of the group, where all 3 sides and all 3 angles are completely different. Take a breath, look at the given data in the question, and decode which one you're dealing with.
When comparing triangles, examiners love to test your understanding of congruence versus similarity. Congruent triangles are identical twins, exact same side lengths, exact same angles. When the command word says prove, you use specific acronyms as your evidence, like SSS for 3 equal sides, or SAS for 2 sides and the included angle. Similar triangles, however, are totally different. They're like a zoomed in or zoomed out photograph. Their angles match exactly, so they hold the exact same shape, but their sides are just scaled in proportion. Do not mix these up. Section 3, shapes and circles, quadrilaterals, and polygons. Let's expand our playbook. Let's compare quadrilaterals, our 4-sided shapes. Their internal properties vary wildly, and this is prime territory for multiple mark questions. A square is rigid. Equal sides, right angles, and crossing diagonals. A rectangle shares the right angles but only has opposite sides equal. Now, a rhombus is essentially a pushed-over square. Equal sides but no 90-degree internal angles. Parallelograms have opposite equal sides but absolutely no right angle rules. A kite relies on 2 pairs of equal adjacent sides. And a trapezium? It only needs a single pair of parallel sides to exist. You have to be strategic. Memorize these properties so you can instantly extract the core trend from any shape they throw at you.
Any closed, straight-lined figure is a polygon. The naming relies heavily on Greek and Latin roots: pentagon for 5, hexagon for 6, heptagon for 7, octagon for 8, decagon for 10, and dodecagon for 12. But listen to me. Here is the most important takeaway from this slide. If you see the examiner use the term regular polygon in the setup, it simply means perfect symmetry. Every single side and every single interior angle is exactly equal. That one word changes your entire calculation strategy.
Let's smooth out those straight lines into a circle. The outside boundary is the circumference. The radius runs from the direct center to the edge, while the diameter goes straight across the middle. A chord connects two edge points without needing to cross the center. An arc is just a curved perimeter piece. A sector? Think of a slice of pizza, bounded by two radii, and a segment is the area sliced off by a single chord. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 4. Folding into 3D, nets. Let's add some spatial awareness to our tactics. Imagine taking a cardboard box and carefully cutting the edges to lay it completely flat on the floor. That flattened, two-dimensional plan is what we call a net. It shows all the faces of a 3D shape opened out. For example, 6 joined squares form the net of a cube. A rectangle with 2 circles attached at the ends is the net of a cylinder. It's a brilliant mental exercise, looking at a flat plan and visualizing it folding up into a 3D reality. In the exam, visualizing this quickly saves you precious time.
Section 5. Construction and scale drawings. This is where theory becomes hands-on execution.
Here is how to literally construct a perfect triangle using nothing but a ruler and a compass. Say the command word is construct and you need sides of 8, 6, and 7 centimeters. Step 1. Draw the 8 centimeter baseline accurately. Step 2. Open your compass to exactly 6 centimeters, place the point on one end, and sweep a clear arc. Step 3, adjust to 7 centimeters, place it on the other end, and draw an intersecting arc. Step 4, connect that exact intersection point back to the ends of your base. And listen, do not erase your compass arcs. The examiner needs to see that evidence to award you the marks. You've just mathematically guaranteed a flawless construction. Building on that precision, we have scale drawings. A scale drawing keeps everything perfectly in proportion, just shrunk down to fit on a piece of paper. This is the structural foundation of every single map and architectural plan in existence. To master this topic, you have to completely understand how to convert measurements back and forth between a tiny drawing and massive real-life distances.
All right, let's do a quick interactive workshop challenge. I'm putting a mental 60-second timer on the clock. Imagine looking at a map with a scale of 1 to 10,000. You measure the distance between 2 buildings on the paper, and they are exactly 1 centimeter apart. How far apart are those buildings in the real world? In meters. Look closely at the units. Think about the conversion for just a second. Don't be like Sam and rush the final step.
Time's up. The correct answer is 100. Here is the exact logic to get full marks. A scale of 1 to 10,000 means 1 map centimeter equals 10,000 real-life centimeters. So the true distance is 10,000 centimeters. But check the command requirement. We need meters. Since there are 100 centimeters in a single meter, you divide 10,000 by 100, giving us exactly 100 meters. It's a simple conversion, but absolutely essential for accurate real-world planning and grabbing those final marks. We have covered a massive amount of ground in this explainer today. We started by defining the sharpest angles, built identical triangles, unlocked the properties of quadrilaterals, folded flat nets into 3D reality, and finally mastered real-world scale conversions. Geometry isn't just a textbook chapter. It is an incredibly powerful toolkit. If you decode the command words, structure your evidence, and manage your time matrix, you will guarantee top marks. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.